and we're going to talk about solving linear equations via the undetermined coefficients method. So this is example 1 on the list of sample problems I included. dy dt equals negative 4y plus 9e to the negative t. Now, this is the system every time we do an undetermined coefficients problem is we have to look at two things. The first thing we want to look at is the constant attached to y. So when we have that constant attached to y, notice in this case that constant is negative 4. So that allows us to think about an associated simpler equation, the associated homogeneous equation, which would be of the form dy dt equals negative 4y. Now, in order to do this, I always have to make sure for this part that I've got that associated equation written with the number times y on the right-hand side. So I need to convert my equation if it doesn't start out in that form. The next thing I'm going to do is then get the associated solution to this. And this is what I often call my y sub h part. So it's the solution to the homogeneous equation, and thus the y sub h notation. So y sub h of t in this case, or y sub h of x if we were using x as our independent variable. And these are the ones where you can go by memory. It's always going to be generic constant, k or c, whatever your favorite constant is, times e to the negative 4t. So in general, that's always the case. Whatever the coefficient on y is, when we've written it as dy dt equals number times y plus function, then that homogeneous part is k equal to the negative 4t. And remember, this is going to be the first portion of the eventual solution to my non-homogeneous equation once I account for the second term. So then I have to go and I have to kind of consider the second term here. I often think it is easier when solving these, especially since we're in the habit of doing that for integrating factors, to go ahead and go rewrite the equation with the y term on the other side. And then the generic guess I'm going to make is always going to be a multiple of the original, that right-hand side term. So unless it turned out that the coefficient on the exponent here on t was the same, so look and notice that here we have a negative 1 on t, and this is a 4. So if the coefficients were the same here, there would be, we'd have to be a little more careful. But if they're not with the exponentials, then it's as simple as making sort of the most lazy guess we can. I'm going to go ahead and erase that green. So what I'm going to do is I'm going to guess that there is a function yp of the form, our right-hand side right now is number times e to the negative t. So I'm going to take a guess that there's some other function of the form number times e to the negative t where I don't know what that number is a solution to this equation. And the reason I'm going to guess this is that if I'm going to take a function, multiply it by 4 and add it to its derivative and get back a multiple of e to the negative t, then there had to be e to the negative t's in the function itself. Okay, so now what we're going to do is underlying, assuming that that really is a solution to this equation, I'm just going to set up what the left-hand side of the equation would look like in this case and set it equal to the right-hand side I'm given. So if that were the case, then yp prime, the derivative of yp, would be a times negative 1 e to the negative t, or negative a e to the negative t. So there we have the derivative of yp is negative a e to the negative t. And so we're going to stuff this into the left-hand side of the equation. So we look at the left here, this part, and we're going to make our left-hand side look like that. So we need yp prime plus 4y p. And so in this case, that would be negative a e to the negative t plus 4 a e to the negative t. And we're going to set it equal to the right-hand side. because if we're saying it's a solution, then we're saying it should equal what the right-hand side of the equation is. So that should equal 9e to the negative t. So in this equation case now, all we're going to do is combine like terms. On the left, we get 3a to e to the minus t equals 9e to the minus t. And therefore, 3a must be 9, and so a is 3. So what this is telling us is that I stuffed that into the equation and this function that I said was a solution, and say 3e to the negative t is a solution to my equation. And so the linearity properties told us that to build your general solution, you just take this one solution you found via this method, and you're going to write it as the homogeneous one. So we're bringing that down. K e to the minus 4t. So for every homogeneous solution, I'm generating a new solution added to the non-homogeneous part. So this gives me a general solution to the differential equation, and I think it can be worthwhile verifying why this works. So I'll verify it for this case. We verified it generically, if you'll recall, in class. So let's just verify. Y prime, oh, I used an x there, it should still be t. Y prime equals negative 4k e to the minus 4t minus 3 e to the minus t. That's y prime. And so now what I'm going to do is I'm going to add 4y to that, and I'm going to see if I get 9 e to the minus t left. So 4y would be 4k e to the negative 4t plus 4 times 3 is 12 e to the minus t. So this line, I literally multiplied my y by 4. And now what I'm going to do is add those two together so that I can verify it equals what the right-hand side is supposed to equal, that 9 e to the minus t. So you'll notice that the k term, the terms with the e to the negative 4, this term and this term, they're going to cancel each other out. So we get y prime plus 4y equals, that term ended up being 0, and then we have negative 3 e to the minus t plus 12 e to the minus t. That leaves us with 9 e to the minus t, which is what we wanted to show. And so we verified that this is a solution to the equation.